this is a work that is very new, because I thought that most of you have already heard me talk about covariant bit threads many times. And so this is an idea that I started thinking about only a few weeks ago. And so it's very much work in progress. Well, we'll see how far it gets. So to motivate it, the motivation is always pretty much the same for me. It's to sort of understand holography deeper and understand in particular how does the dynamical space-time emerge from some more fundamental description, in this case the CFT degrees of freedom. And of course the types of questions that we want to ask is, what is the structure or characterization of CFTs, and within the CFTs of states that would have gravity duals. And in particular, in terms of the recent understanding, or at least thought processes of entanglement building geometry in some sense, how does that actually happen? So the motivation is to try to understand these issues better. And one of the early hints we had that entanglement has something to do with geometry was that, well, the bulk description geometrizes entanglement very conveniently, in the sense that these various entanglement relations that are very fundamental from the quantum information standpoint are extremely easy, almost trivial, to prove geometrically within the bulk description. So that's great. On the other hand, at the same time, this holographic recasting obscures certain things. For example, it obscures the fact that while, for example, strong subadditivity is, true generically, while monogamy of mutual information is not, the geometric proof for both of these looks pretty much identical. So how is it that the geometry doesn't really distinguish between two relations which from the more general standpoint are very different? One is sort of completely universal and the other one is very restricted. And so once we understand, for example, answer to this question, that will give us a little bit better insight about, well, on the one hand, the essence of these holographic entanglement entropy prescriptions, but on the other hand, at the same time, on how does actually space-time emerge from them. Okay, so that's the motivation, and just to give you a preview, so that for the experts in the audience, everything that I'll say later will be pretty much on this slide, so you can doze off or whatever. For the students in the school, it's just a preview. There will be some jargon that maybe you haven't heard yet, or acronyms, so don't worry about that because I'll go through that all in more detail later. But the preview is to ask this question: why does strong subadditivity and monogamy of mutual information look pretty much the same from the bulk standpoint, in particular in sort of the RT prescription of, or HRT prescription of computing entanglement entropy? So one statement to say, right, at the outset is that, well, it looks the same only at the geometrical level, at the leading order n squared terms, where in a sense you end up canceling surfaces and then the two relations become the same. And one might say that, okay, so maybe that's not so interesting, but one can still ask, is that the full story, or is there already a distinction between these two already at the geometrical level that somehow the HRT is not sensitive to? Okay, and one hint that that may be the case comes from a different, still geometrical, but different reformulation of the holographic entanglement entropy via what Hedrick and Friedman called bit threads. And so a hint from bit threads is that, in fact, within that, prescription, the strong subadditivity is completely trivial to prove, while at the same time, the monogamy of mutual information has not been proved yet, has eluded proof. Well, it's not yet. Okay, so I'm going to provide one proof. Matt and company have observed that if you assume a presence of something that they, I believe, called cooperative flows, then MMI follows trivially. Okay? So the question that I ask here then boils down to what guarantees in the bulk the existence of such cooperative flows generically. And my answer that I want to propose today is that the answer is bulk locality. That it's really due to bulk locality that's essential for proving MMI, but not actually essential for proving strong subadditivity. Okay, so that's the preview. So after this, I'll sort of give a little bit of a quick background, and then the main part of the talk will be the argument for how do you prove MMI in using the bit threads, and then how far can we generalize and so forth. So let's start with the background. Okay, so Tadashi thankfully gave a great introduction to holographic entanglement entropy, so I don't have to go through this again. So this is just to remind you by the pictures, the entanglement entropy of some region that you can use to bipartition the boundary Hilbert space is given by the area of the minimal surface that's anchored on that region. And you can, of course, covariantize it, which is necessary in time-dependent situations, where now instead of a minimal surface at a constant time slice, so this is the time picture, you have an extremal surface that's anchored on this boundary. So within that picture, strong subadditivity is very easy. So again, Tadashi mentioned that yesterday. Strong subadditivity just tells us that the amount of correlations is monotonic under inclusion. So this is the actual relation. So if you have regions A, B, C on the boundary of ADS, the entanglement entropy of AB is the area of this surface, the one of BC is the area of this surface, and that's bigger than the areas of B plus ABC, simply by noticing the fact that this was the minimal surface anchored on this region. So in particular, its area is bigger than the area of this one, and smaller than the area of this portion, and this area is smaller correspondingly than the area of this. Okay, so it just follows directly from comparing the areas. Now the monogamy of mutual information, which you can think of as sort of superadditivity of mutual information, is this expression. And, well, you can make a choice of, well, either there is zero mutual information between A and C, or between sort of B and the complement of ABC. So let's just choose, without loss of generality, to fix this guy to have zero mutual information, in which case the entanglement entropy of AC is in fact the entanglement entropy of A plus entanglement entropy of C. And so these three terms, in fact, cancel out of the expression, and what remains is again the same thing as we had before. And so the proof is identical. Okay? So within this RT prescription, there isn't any difference between the two proofs, And you can say the same thing in the time-dependent situation. So Aaron proved both of them by a more sophisticated argument using the max-min prescription for these extremal surfaces. But again, the same proof goes through. So there is that holographic prescription for the entanglement entropy does not distinguish between strong subadditivity, which is true universally, and monogamy of mutual information, which is true certainly for holographic states, possibly more generally, we don't know. Well, actually that's not true. I mean, you can find things that are not geometric that satisfy monogamy of mutual information, for sure. But it's certainly guaranteed for geometrical states. But the bulk doesn't, give you any hint. This prescription doesn't give you any hint for, what's the difference between them. Okay? So the bit thread picture is a different reformulation of the holographic entanglement entropy, which, so this was coined by, by Hedrick and Friedman a few years ago. And the prescription is as follows. So you can describe the entanglement entropy of a given region in terms of a flux of a certain flow, a vector field, which is divergence-free and of bounded norm. So Matt and Margaret called these things threads, bit threads, the integral curves of this vector field. And the entanglement entropy is just the maximum such flux. So you can equivalently think of it as a flux of some maximizer flow. This maximizer flow is not unique, but it's any maximizer flow that maximizes this flux. Its flux is the entanglement entropy. So this is equivalent to the Ryota-Kanagi prescription in terms of the area of the minimal surface by using the max cut, the max flow min cut theorem. And you can derive that using something called the Lagrangian duality, which I won't go into, but if you want the details, this is what we explained in great detail recently with Matt. Okay, so the intuition behind this is that the entanglement being counted by the number of these bit threads, and these bit threads can't end in the bulk anywhere. Once they start on the region, they have to keep going and end somewhere else on the boundary. And they can't get arbitrarily dense. You can think of them as having some thickness. And so you want to pack as many of them as you can coming out of your region. And of course, how many you can pack depends on how big the bottleneck is of this flow. And the bottleneck is precisely the minimal surface. And so since the minimal surface gets the threads maximally packed going through it, the number of them is equivalent to the area of that surface. Okay, so that's the intuition behind why these two prescriptions are equivalent. But although they're equivalent, this is quite a useful reformulation of the holographic entanglement entropy because, well, in many senses, it behaves sort of much more naturally. For example, the minimal surfaces can jump to different space-time regions under continuous variations of the region on the boundary, whereas the configuration of the thread can vary continuously with continuous variation of the region. It's just a bottleneck jump somewhere else, and so forth. It's also computationally more efficient. It sort of has better ties to quantum information notion of many of these quantities. And so in this sense, it provides a bit more intuition. Okay? Sorry?
How do you efficiently compute the maximization step?
Well, you can translate it to a sort of a linear programming context. And so it's a...
I mean, a context where I just divide into some finite number of segments and I'm keeping track of just the flow.
You can flow, yeah. You don't get stuck in some local minima. All right, so that's the bit threads. So just to say a little bit more about this interpretation business, let's see, how much time do I have? Or how much, sorry, I should ask. 15, okay. So one observation is that you could have a common maximizer flow for regions which are nested, but not necessarily, generically you don't have a common maximizer flow for regions which are, for example, next to each other, because that would, they might, the flow from them might interfere excuse me, with each other. So, but you can have it for nested regions. And so you can maximize, for example, on A, B, and then you have a choice whether to maximize on A or maximize on B simultaneously, but you can't do both. And so from that observation, you can sort of have an interpretation of quantities like conditional entropy or mutual information in terms of the behavior of these threads. So this is taken from the Friedman and Hedrick's paper directly, so they sort of explain these very carefully, but basically you can think of the conditional entropy as sort of the number of threads which would be left on the first region when we would maximize on the second region the mutual information of the number of threads that can flop between the two regions. So in this case, both of those would be 1. For quantum states, you can have the conditional entropy actually being negative, and so as in this example, and then you have some genuine quantum entanglement, which is measured by the number of threads which go between the two regions and so forth. So this is a very nice picture. So when you want to prove things like strong subadditivity, it falls out almost immediately. If you rewrite it in terms of this conditional mutual information, you can think of this as the sort of the maximum flux on some region after you maximize on two nested regions minus the minimum flux on the region after the same maximization. So since it's a difference between a maximum and minimum flux, or equivalently the number of threads that you can sort of flip between certain regions, that's manifestly positive quantity. Okay, so there's a little bit of thought involved in sort of equating the conditional mutual information to sort of this prescription. But once you have done that, the fact that the conditional mutual information is non-negative, which is the statement of strong subadditivity, just falls out immediately. On the other hand, you can't do the same for the monogamy of mutual information because, well, and in particular, you can, if you construct the nest situation, fluxes, which obey all the nesting properties, all the requisite things that were used in these arguments, you can still find states for which the MMI is violated. For example, something that's, that can be created from a simple GHZ state. Okay, so some more ingredients are needed for this. Okay, and the ingredient that's needed, I am now going to explain what that is, but that will be the bulk locality. Yeah, go on.
Didn't you argue before that this bit thread picture was equal to the Veronika picture?
It is equivalent by the Lagrangian duality. Nevertheless, okay. So okay. So what you can, of course, do is you can dualize to Ryutakanagi, prove MMI there, and dualize back. There doesn't seem to be anything that's, well, hitherto there didn't seem to be anything more direct. Okay, that's the statement I should have said. Unlike the strong subadditivity, this one doesn't follow, this one is not at all like dualizing back to Ryutakanagi, comparing the areas and dualizing back.
You said that there was a state that violates the mutual state of qubits, right?
It's a state of qubits that follows the ingredients that went into this, nesting and things like that. Okay, so it's not a geometry. Of course, when we using the Lagrangian duality, we are already using some geometry. And within the geometry, yes, of course, MMI is necessarily satisfied. Yeah, I should have said that clearer. Okay, so what is the argument within the bit threads? Okay, so this was the statement of MMI. So if we consider the left-hand side, you can write it in terms of the flows as just integral over the given set of regions of any maximizer flow for those regions. That's what these V's mean. And because they're maximizer flows, they necessarily have larger flux by definition than arbitrary flows. Okay, so these V1, V2, V3 are some arbitrary flows integrated over the same sets of regions. So that necessarily gives this inequality. Okay, now you can split it up into these regions to have this equivalent set of integrals. And what we want to do is to relate this expression to something that would allow us to relate it to the right-hand side of MMI. And well, it's easy to see what you want to do. You want basically to have this V2 plus V3 be equal to VA plus VABC, this guy be VB plus VABC, and this was VC plus VABC. So it's very easy to solve for what you want, and in particular, this is what you want. You want these V1, V2, V3 to be expressions that look like this, so that when you plug it in, you get precisely the right-hand side of MMI. Okay? So the proof of MMI would hold, provided, would be pretty trivial, provided you can show that these guys in fact are flows. So far, each of these terms, VA, VB, VC, and VABC, were flows, but that doesn't guarantee that the expressions, that these combined expressions are flows. In particular, what it doesn't guarantee is that they satisfy the norm bound. The divergence-free bound follows immediately because by linearity, but the norm bound doesn't follow because you have half of something that could go up to, each term can go up to 1, so this could go up to 2 in various regions. And so what you need to do is to show that, well, you need some enough cancellations such that, in fact, you can construct, for arbitrary choice of ABC, you can construct such maximizer flows so as to have all three of these guys being simultaneously flows, meaning simultaneously have norm bounded by 1 rather than 2. Okay, and the obvious things are not so easy. So for example, you can't just say, well, let's just cancel VA with VB to take care of these two terms, then you're just having an average of 2 flows, which is a flow, and then something here. That doesn't work because, as I said before, you can't have VA being VB at the same time because VA and VB are not nested. You could have VABC equal to one of these three, but not all of them. And so, again, that's not enough to make sufficient cancellations. Okay, so the proof that I'm about to give shows you how to do this construction to guarantee that, in fact, all of these can always be made into flows. Okay. So the construction starts the same way as before. Let's just do the simple case of ADS3. We partition the full space into A, B, C, and the complement. We find the corresponding minimal surfaces and the ones for these combined regions. Okay, so this is the same setup as we had before. And now what you want to do to construct flows that would allow you the sufficient amount of canceling, the trick is to try to make flows that, that would cooperate. Okay, so you can think of a flow from A as separated into multiple strands, one that goes into B and one that goes into D, assuming that A and C is smaller area than these two, so you can make a choice whether to have flows going from B to D or A to C. So if AC is smaller, then you have flows like this, but you don't have to have flows like that. Okay, so you can separate this into these multiple flows, and you can use the same strand as part of a flow from A into B or from B into A. It's the same strand, you just change the directionality. Okay? The norm bound and the divergence-free bound is guaranteed to hold for one if it holds for the other. Okay, so you can check very easily then. Well, so what one wants to do then is to make sure that these strands are confined into separate bulk regions, non-intersecting bulk regions. And if that is the case, then you can check very easily that, well, if you separate each of these maximizer flows into these strands in these different regions, the A, B, C, D, E are just these regions that are accommodating these different strands, then our putative flows indeed everywhere in the bulk spacetime are given by things that were manifestly flows. So even though each of these guys is a sum of multiple flows, they never interfere. They never intersect in the same region. And therefore, they're always, everywhere they satisfy this norm bound. Okay? So they all are flows. Okay? So you have to guarantee that you can separate these strands into separate bulk regions. So that's the crux of the argument. How can we ensure that that is possible? Okay, so the most constraining part of those flows is right through the bottleneck. And so first thing to check is that the areas of the minimal surfaces can be partitioned in such a way as to be consistent, as to allow all these flows. And that you can check easily applies because the relations that you have on these areas for these strands, well, you have 9 equations for 10 unknowns, so you in fact have a 1-parameter family of solutions. So you still have plenty of freedom in constructing such things. And away from the minimal surfaces, they're less constrained. Now, this is something that I didn't have time to do in preparing my slide, and it's, I guess, a little bit of a technicality in GR, so I'm not going to go into details, but I'm happy to explain why is it that when we have ensured that we can make this combing of these flows consistently on the bottlenecks themselves, that we don't have to worry about these regions intersecting somewhere else. And I'll just say the argument in words. One way you can construct these strands is to use foliation by minimal surfaces in the bulk, which has the following job. So if you have a strand that's normal to a minimal surface, by definition of a minimal surface, the expansion of the normals to it is 0. You know, the minimal surface doesn't want to bend one way or the other, so the expansion of the space-like normals to it is 0 at that surface. So the areas you go away along these threads from one minimal surface to the next doesn't change. And so the threads stay at maximum density throughout this foliation. So it's like combing these strands to be maximally dense, have norm 1, everywhere rather than just on the bottleneck. And the argument then utilizes different foliations by these different minimal surfaces to comb these flows in such a way that you can show that, well, once you comb them, once you separate the flows through the bottleneck, it's necessarily steers away from each other elsewhere. Okay, so that's the summary of the argument. There are actually a couple of different constructions that one can give. One utilizes multiple foliations, one for each thread. Another utilizes foliation by partial minimal surfaces. So neither of them uses, the full minimal surface foliation, but just parts of it, which is where this bulk locality creeps back in. Okay, so you can generalize this in various ways. And now let me ask again, how much time do I have now? No, sorry, I wasn't keeping. Okay, so I'll just say in words. So it's easy to generalize this for any configuration of this ABC that I had, and similarly for deforming your three-dimensional geometry, because the whole thing was rooted on these minimal surfaces not intersecting. More interestingly, you can ask what happens in higher dimensions. There it looks like the same argument. Well, there the minimal surfaces need greater degree of specification rather than just the endpoints. So if you have larger set of families of foliations, but it's still true that they're nested, so you can still foliate. And in fact, in more dimensions, you can have the threads sort of go around each other. So it seems like it's easier to implement this in higher dimensions. But I haven't, dotted the I's and crossed the T's on that. Similarly, it would be very interesting to check what happens in the time-dependent situation, where now we have to use the covariant bit threads. Again, the covariant bit threads are still one-dimensional objects, even though you have the time dimension. So again, it looks like you have higher freedom because the threads could now cross in sort of the temporal direction. And finally, you can ask what happens for more partitions. And this is really interesting because, for example, in the five-party cyclic inequality, you can try to play the same trick. And there is a new ingredient here, but I think the same method should still work. Okay, but again, this is subject to be confirmed. It's still work in progress. But the new ingredient here is the following. So you could show this inequality holding provided these constructions are flows if each of these are maximizer flows. But now we have maximizer flows that are going through, for example, AB simultaneously with going through BC. And so you can't use one set of strands to implement both at the same time, because our threads were to be maximized on AB, so they had to be perpendicular to the AB minimal surface, so they can't be perpendicular simultaneously to the intersecting BC minimal surface. So you have to use overlaid set of strands, and then the analysis of the separation into the different bulk regions is a little bit more complicated. Okay, so, but on the other hand, once one can show that this still goes through, one can start to understand how the bulk locality features in all these other multi-party inequalities, entanglement relations that likewise don't hold for general quantum states, but do hold for holographic states, for states with a gravity dual. Okay. So let me conclude. Let me just summarize first. So I have demonstrated the existence of these cooperative flows, at least in this simple case. And the crucial ingredient here, just to repeat, was this bulk locality. The construction, which I very quickly just sketched for you, used foliation by piecewise minimal surfaces, which allowed us to comb these threads into the strands that were cooperating with each other. And so from this standpoint, this bit thread prescription ended up being more useful than the prescription in terms of the areas of the minimal surfaces or extremal surfaces. And so it revealed, back to this question of SSA versus MMI, it seems that the SSA didn't really require the cooperative flows. It's more general, whereas MMI, because it did require them, really does hinge on bulk locality much more directly. Okay, so there are many open questions, and maybe, I guess in the interest of time, I should just leave them out there, but one could ask, what is the, how far can you generalize? What is the role of time in this bulk locality emergence? Is there even better reformulation than either Ryota-Kenagi or this bit thread that would be get us closer to understanding this bulk emergence? Can we use this to map out the full holographic entropy cone? Are there other measures that are not based on the bipartite entanglement that would play any role? And also, it's very suggestively related, at least bounded by this entanglement of purification that Tadashi was talking about yesterday. So let me end there.
Sorry, question?
Just as a mathematical question, does MMI hold for a general flow problem? If we have a general graph with boundaries A, B, C, does it hold?
No. No. So I think that's the thing that was illustrated in Matt Hedrick's and Friedman's paper. So they constructed examples where MMI did not hold by explicit evaluation.
Of flows.
Of flows.
Okay, thank you.
In this graph, like.
So let me ask a modified version of Alex's question. So how about with tensor networks? So with at least some, I guess there in principle it's supposed to depend on the tensors, whether MMI is true or not. Is that the right statement, or is there something?
I'm not sure. I'm sure somebody in the audience must be much better expert on this.
Yeah, I thought that, for example, like in these people with the holographic entropy con, it was, they wanted to generate things and saturated these holographic qualities, and I believe they had to use the tensors for that. I'm actually not an expert. Yeah, so I guess I was wondering, so you had this, consistent was the word you used?
Well, cooperative. I thought that was the
so
thing that Matt coined, but I'm not sure whether he's
many,
still using that or not.
So yeah, it'd be nice if there was some interpretation of this cooperative grid. Because actually the original bit threads, even I think were found first in tensor networks. And so I would guess if there's some additional structure to put onto the bit threads, maybe it has some nice manifestation for tensor networks also.
Right. That's a good. That's a good idea.
Okay, so if there are no more questions, we thank Veronika again.